whatever.
Okay, welcome back to our second day. We'll have Mark Hughes for the first time. Thank you. And if you haven't registered, because I think we have a couple of people missing, if you haven't registered, please do it and also type your name tag so that we know everybody is here.
Thank you. Thank you all for coming back for day 2 of my talk. I drew the same picture on the board as I did last time, and I'm not going to forget to talk about this quickly before we jump into the main topic today. Remember on the first lecture, I just wanted to kind of come back and address this question that kind of came up in the first lecture about the framing of these. Remember, we're forming ribbon knots, and so we do that by sort of picking a bunch of unknotted spheres, and then we find a bunch of arcs that sort of like connect the spheres to themselves and may link some of the spheres. And there was this question about framing, and we kind of, discussed how it's kind of only a Z2 framing that matters. But there's kind of a nice geometric way to maybe see why the framing along these arcs doesn't really have any difference, as long as you're assuming that the surface you end up with is orientable. So suppose that I've sort of set up my ribbon 2 knot like this, and I've connected a bunch of arcs with their endpoints on the spheres. And if I want to thicken these up to sort of 3-dimensional tubes, I can do that. Now there's, as you mentioned, there's twisting that can happen, but as long as you assume that these things are connected in an orientable way, the exact number of twists doesn't matter. And the reason is you can, in sort of 3 dimensions, we can imagine sort of a tube where we've affixed the blackboard framing along this tube, and maybe it had a single kink like this. Well, this is sort of a picture that makes sense in 3 dimensions. If we were to undo this kink, then we get sort of a full twist like this in our framing. However, what we can do is, instead of thinking of this as being in 3 dimensions, we can actually take a little segment of this and push it into the 4-ball. And as we push it into the 4-ball, that gives us the freedom to sort of pass this piece through the other one. And so within the 4-ball, we can sort of change, we can change a crossing like this. Okay, so we take our single kink with the blackboard framing, we push it into the 4-ball a little bit, we're allowed to sort of undo or change that crossing. So when we push it back into the 3-ball, we now have a different crossing. And so when we undo this kink, we now have changed our framing. And so so you can kind of, as long as it's orientable, the exact number of twists doesn't matter, because by pushing it into the 4-ball, you can always change that through a modification like this. Any questions there?
A little comment. Another way to say that is, in 4D, the normal bundle is something 1-dimensional. Is going to be D3s, and pi 1 of SO3 is Z mod 2. That's the geometric proof.
Exactly. Cool. Well, so today we're gonna, the main topic today is not this. The main topic today is going to be talking about banded and linked diagrams in 4 manifolds. So we essentially want to sort of extend the stuff we talked about to surfaces within an arbitrary 4 manifold. And we want to sort of come up with geometric ways, or at least very concrete ways, to represent surfaces that are embedded in 4 manifolds. So that's our goal today. Okay, we want to extend banded unlinked diagrams to surfaces in arbitrary 4 manifolds. Okay, and for my purposes today, X is always going to be a closed, oriented 4 manifold, smooth 4 manifold. We're going to use smoothness in a because we want to assume that everything we work with has a nice smooth handle decomposition. Now, if you remember last time, I mean, you can maybe think a little bit about what might we represent a surface via a banded unlink in a 4 manifold. Now, if you remember last time, when we sort of came up with our banded unlinks, we had some picture like this. Then maybe we had some picture like this. Oh, I didn't plan that one well enough. Something like this. Who knows? Now you can see now why I draw pictures in advance on PDFs. Let's name phrases. the point is, I have better pictures to show you today, but that was on the fly. So the point is that in our core manifold, remember that picture of like, sometimes we want to push all our bands down to the same level. And in R4, we have sort of a naturally well-defined height function. Just pick one of the coordinates to be sort of your height function, and you can sort of adjust things with respect to that. For an arbitrary four manifold, generally it's not equipped with a natural height function, so we need to sort of affix some extra structure. And then we want to know sort of how does the sort of the decomposition of our surface respect the decomposition of our four manifold with this extra structure, okay? So this extra structure is going to come in the form of a Morse function. So we're going to let H be a self-indexing Morse function. Okay, and what do I mean by self-indexing? I mean that essentially critical points of index K live at height K. So critical points of index K live at height K with respect to H. So maybe a quick schematic would be in order. We've got our four manifold X. We've got, this is not going to be enough room. Let's do it on the chalkboard here. So we've got our four manifold X here. There's lots of interesting topology. It's kind of an oval. Okay, and so our four handles live here. Our three handles, I'll use capital H for handles because H is my Morse function. And so when we look at our critical points under our Morse function, so this is H, we get our four handles living at height 4, our three handles at height 3, and so on. Okay. So is everyone okay what I mean when I say a self-indexing Morse function? It's going to be kind of important just because we want to organize things in a way where we know all the critical points of a certain index are at a given height. So any questions on the setup here? I should also say that I'm going to assume it has assume X has one handle. Okay, and so technically, so I'm assuming here that my four manifold is zero handle. Yes, correct. I'm assuming that my four manifold is connected, and so as long as you have a connected four manifold, you can always use one handles to cancel any extra zero handles you have, and you can assume that you have a single zero handle to deal with. Okay, so have a room. Nice. Okay. So I want to just say a few words about handles. Okay, I'm assuming most everyone here has seen handles. We're going to kind of think about them in terms of like the gradient vector field that's induced from our function. So it's worth kind of drawing our handle pictures because we'll come back to them and kind of look at how this vector field looks like, what this vector field looks like on our manifold or on our handles. So I'm going to just kind of do a little bit of a detour into handles, or at least handles, four-dimensional handles. So recall an index K four handle is really just a copy of a K ball times a 4 minus K ball. So we're just taking a K-dimensional ball and we're thickening it up to be a 4-dimensional ball. And we think of these things as being attached to a 4 manifold along the boundary. So say
you want to say 4-dimensional and
yeah. No, sorry. Yes, let's say this correctly. So a 4-dimensional K handle or another way of saying that is a four-dimensional index K handle. So I kind of mix those two terminologies. So yeah, four-dimensional index K handle is a K-dimensional disk that we've thickened up to become four-dimensional. And we think of one of these things as being glued to a four manifold with boundary by specifying an embedding of, so it's attached to a four manifold, which we'll call Y, along an embedding, which I'll call psi, where we take the boundary of sort of the K factor, and we glue it into, we map it into Y via some embedding, okay? So again, we're sort of, I'll draw a picture or two here in a second, but we're sort of focusing only on the boundary of this handle, or we're taking sort of a subset of the boundary. Maybe it's worth drawing. Oh, that's the one that doesn't come down. I'll leave that up here. So let me just show you sort of some pictures here of 0, 1, and 2 handles. So a 0 handle, a four-dimensional 0 handle, is going to be B0 times B4. So it's essentially just B4. Now I still can't draw four-dimensional balls, but I'll draw a three-dimensional ball and let you imagine that it's got one extra dimension. The attaching region so this is the thing that we would sort of use to glue this four-dimensional ball into our manifold. Well, our attaching region, in this case, really my handle. Okay, so my handle is really just B0 times B4, okay? So the attaching region is going to be the boundary of B0. So this is just empty, okay? And so the way that I glue this in is I glue it in as a disjoint union. Okay, so when I'm gluing this into my four manifold, I'm just really setting it next to my four manifold and not really attaching it to anything. A one handle looks like B1 times B3. So again, cheating and dropping the dimension down a bit. I'm gluing this handle in by the attaching region. And so here my attaching region is going to be the boundary of B1 times B3, which is really just S0 times B3. So this is just this part here. I'll color it in green. So that it's the boundary of the B1 direction here times this thickening factor. So this is going to be my attaching region here. Okay. And so so when I glue this in, what I have to do is I have to specify where in my four manifold, or the boundary of my four manifold, am I going to attach the feet of this one handle. Okay, so you can do that in sort of two different ways. Sometimes you'll sort of specify by drawing the feet of this two handle in the boundary diagram. And so here you'd sort of specify where these two green free balls are going to go. And then you'd sort of like imagine your one handle's been attached on top of that. Or you can kind of squish these three balls together. And this is kind of the same thing as oftentimes the notation is just using these one handle circles. And you can think of this one handle circle as being like obtained by squishing your two free balls together. Or you can think of it as sort of removing an embedded disk from whose boundary is the circle from the interior of your four manifold. Okay, so this is kind of the notation we'll use in our diagrams, and you can think of that as being sort of specifying the location of attaching the one handle, which is the same thing as drilling out a two handle from the interior. Any questions there? Okay, And then the last one that we'll need to really work with are two handles. So these are B2 cross B2, and here our attaching region is going to be the boundary of the first B2 thickened up. So that's going to be S1 times B2. And so a two handle, try and draw it big enough because I'm gonna kind of enhance these pictures with a little bit here in a second. Okay. And so here my attaching region is this S1 part that we've thickened up. And so when we glue this in, what we have to do is we have to specify where this S1 cross B2 goes in our four manifold boundary. And so to do that, we have to specify some knot in our diagram. And because this boundary has a framing, we have to specify, we usually specify that framing by some integer. And so we'll attach some integer framing here. Okay. And that sort of denotes the pattern along which you're going to glue the boundary of this two handle. So you sort of think of this two handles being glued there. Okay. Any questions on this? Yeah.
Sorry, I kind of missed what you said about the yeah, that one.
One handle?
Yeah, what was that picture to the right?
This one?
Yeah.
Yeah, so it takes a little bit of thinking maybe to like convince yourself that adding a one handle is actually the same thing as removing a two handle. You can kind of think of like a two handle as being glued along the one handle, and if you do that, they just cancel each other out. So sort of adding a one handle is the same thing as removing the canceling two handle. And so in this picture here, we draw a circle, and instead of sort of interpreting it like this picture here, where this is telling you where to glue a two handle, this is really telling you where to delete a one handle from the interior of what you've already built.
Okay, so but the circle, then can we also draw a knot to mean or?
No, so these dotted one handles are always unknots. And so the dot sort of tells you that it's to distinguish it from a two handle.
Is it always an unknot because the complement of the one handle will always be an unknot, or?
It's always because like if you're canceling, if you're sort of looking at it in this way and canceling a pair, like a one handle and a two handle, you're canceling it along an unknot in the boundary.
Okay. I think it makes
Does that make sense? It's like that in order for this cancellation picture to kind of make sense, you want it to be, it has to be like an unknot to cancel.
kind of makes sense. I'll think about it. Yeah.
Okay, okay.
Can I ask another question?
Yeah.
So does the circle in the second picture, is that like the attaching sphere of the two handle that you sort of like?
This one here?
Sorry, the picture that.
This one?
Yeah. Is that sort of an attaching sphere of the two handle that you're like I'm trying to figure out what the circle represents in terms of this other picture.
Okay, so the circle, yeah, the circle represents, I guess, like this here. Well, sorry, the circle lies along there. And so if in this like picture where you're canceling a one handle and a two handle, you've got this two handle in place. The circle would be like this, like the attaching region of that two handle that cancels. But then we remove it and sort of to sort of make it clear that we're removing it and not just attaching something new, we draw the circle, the dot there.
Okay.
Yeah. Other questions?
I might just
Oh,
be jumping
yeah.
ahead, but are you gonna just do an example of like going from like the sphere Kirby diagram, the Kirby diagram with the spheres to the Kirby diagram with the dot?
Like to go from
Explicit example.
from this to this?
Yeah.
Yeah, you can, so, oops. Yeah, I can draw an explicit example, I think. It's always dangerous when I haven't prepared it, but, so, yeah, actually I have one more or less prepared, so. So this is a diagram would be a diagram of S4. Oh, well, let me maybe just say what, let me maybe just say really quickly what a Kirby diagram then is. So a Kirby diagram, the nice thing about these handle decompositions is you really only have to, there's, when you then sort of, if you think about what a three handle and a four handle looks like, you end up really just getting these like, sort of bouquets of circles that have been thickened up to be four-dimensional. And by Laudenbach and Ponaru, there's a theorem that says essentially the 3 and 4 handles can be glued in uniquely. So if you specify sort of the 1 and 2 handles, then you just really need to specify the number of, you just need to specify like, I mean, assuming you're working with a closed manifold, for example, there's really only one way to glue in 3 and 4 handles. So you're that's all the information you have to specify. So a Kirby diagram is then just sort of a diagram of S3. So maybe I'll just write this down a little bit more carefully. So if you specify, since attaching 3 and 4 handles is done uniquely, or there's sort of only one way to do that if you're forming a closed form manifold, that implies you really just need to describe the 1 and 2 handle attachments. Okay, and so once you've, so the idea is you start with sort of a picture of S3, which you think of as just being the board you're writing on. Then you sort of describe how to glue on the 1 handles and the 2 handles. And if you've done that, that gives what's called a Kirby diagram of your 4 manifold. Okay, and just sort of as an example, so this will be kind of the example to hopefully show how this one handle business works. Okay, so I can draw this picture in 2 ways. So I've got a 1 handle that I've attached here, which you can kind of think of as coming out of the board. I've got a 2 handle that kind of goes up and over the 1 handle. And then I wanted to add something like this. So I need to add framings to all my 2 handles. So this is 0, and this is -1. And if you add in 2 3 handles and a 4 handle, this picture should give you just S4 back. So this is my 1 handle that sticks out of the board. And I think of these 2 handles as kind of being glued. So, I have a 2 handle attaching region that enters the 1 handle, goes across the 1 handle, and then sort of continues on its way. Same thing happens here. I'm sort of tracing my 2 handles around. So this would be sort of the 2-footed 1 handle notation. If I want, though, I can kind of think of, the way that I think of it is sort of like squishing my attaching regions together. And when I do that, I get this sort of thing here. So I just took those 2 3 balls, squished them together, they became a dotted circle. And now instead of sort of going up and around my 1 handle, these just go through the dotted 1 handle notation.
When should you worry about the framing then? Because like this seems like you're just doing some like isotopy, but you're not actually doing that.
Yeah, so this does get a little bit subtle, because you can kind of like the path in which you sort of draw these like balls going together could sort of be different. And so you do have to be a little bit careful about the framing. So because the way in which you sort of push these balls together could be different, and you could sort of induce some changes in the framing. So yeah, typically I think what people typically do is they sort of when they specify the framing here, yeah, like you sort of think of this as just you think of this as I guess being like a 0 framed handle, I think, and that's how the framing comes. I think so. I'd have to think about that for a second, but so there's some subtlety with the framing for sure when you glue these together.
Right. And so like you can have 2 like Kirby diagrams representing the same 4 manifold, but you just have to show that like the framings will after some isotopy will be the same thing.
Yeah,
Okay.
yeah, like when you say that two Kirby diagrams are the same, it's the underlying link and the framings, yeah, yeah. And there's sort of a little bit of subtlety in like these zero handle framings, or these one handle framings when you do that, so, okay. So, all right, so let's sort of draw a schematic here. Okay, so the point is with one of these Kirby diagrams, if I draw myself a picture here, I've got my 4 handles, my 3 handles, my 2 handles, my 1 handles, and my 0 handle. If my Kirby diagram is self-indexing, then I can if I'm gonna call M sub t, I'm just gonna let that be the preimage of the value t under this Morse function. So I can think of this as being M, this middle level as being M5 halves, M3 halves, and M1 half. Okay. And so when I'm sort of traveling up my 4 manifold, I pass my 0 handle, that's just going to be a 4 ball. Okay. So the boundary of that 4 ball is just a 3 sphere. So I can think of M1 half as just being the 3 sphere, because I've just at that point only passed the 0 handle. When I pass the 1 handles, that's going to correspond to doing 0 surgery. So I won't say too much about that, but you can think of sort of when you add a 1 handle, what happens to the boundary of your 3 manifold? Well, it turns out that that's the same thing as doing 0 surgery. So this is going to be some 0 surgery along the dotted 1 handles. Okay. And then at 5 halves, that's when you've passed the 2 handles. That attaching a 2 handle changes the boundary by doing a Dane surgery along the attaching region of the 2 handles, where the surgery coefficient is determined by the framing. So this is Dane surgery along 2 handles. Okay. So if we think of a diagram like this, if we look at a Kirby diagram like this, which is my 4 manifold, if I sort of ignore the attaching regions of the 1 handles or of the 2 handles and this sort of dotted circle thing, and only look sort of at the complement of say a tubular neighborhood of these things inside S3, that complement gives me a subset, and I can think of that subset as existing either down here, here, or up here. So I can kind of think of, at least in a region that's sort of away from all of these attaching things. For example, I could specify, maybe I should use a different color. I could specify, for example, a link, something like this, and maybe specify some bands. Okay. Okay. And this banded link here, because it doesn't really attach, it doesn't intersect any of the attaching regions, we can think of this link as sort of existing either here, here, or here. Okay. And essentially what we're doing is we're using the Morse function, which induces this handle decomposition, to come up with an identification of these levels here, away from the attaching regions. Okay. So let's write it here maybe. All right. So given a banded unlink, or a banded link anyway, suppose it lives in the complement of, I'm going to call our Kirby diagram sort of script K. Okay. So as long as this thing lives in the complement of a tubular neighborhood of our Kirby diagram in S3, we can think of LB as living in either in any of these levels. Okay, and so maybe actually, yeah, maybe at this point I'll bring down the pictures. I think I have a picture of this. And so the benefit in doing that is now if I draw myself a banded unlink in my four manifold, I can sort of think of it as extending to these different levels and extending in between these different levels, as long as it doesn't bump into the attaching regions of the two handles or the dotted one handle circles. Okay, so let me maybe show a schematic here. Oh, so this would be sort of an example of a banded unlink. The underlying Kirby diagram is the green circle and the dotted purple circle. So the dotted purple circle gives you a factor of S1 cross S3, and then the green one-framed two handle gives you CP2, and since we've just sort of stuck them next to each other, this is a connect sum decomposition. And so this banded unlink gives us a torus inside this connect sum of CP2 with S1 cross S3. Okay. Now, how does this give me a torus? Well, I mean, you can kind of just check A, that it's orientable. You can also check that, oh, perfect. You can check that this is orientable. You can also check that sort of just count the Euler characteristic, the number of components and the number of bands. But how do we turn this into a torus inside this four manifold? Well, here's sort of a schematic, okay? So I'm going to think of my banded unlink as living inside this 3/2 height, okay? Now, by what I just said, I can kind of think of this banded unlink as living in any of these other levels as well, okay? So I can kind of extend my banded unlink sort of up past these one handles and two handles, and we can do that because they don't intersect the they don't intersect the attaching regions of those handles. And so then what we can do is we can kind of think of filling these in now with discs above and discs below. And if this is an unlink down here, then we can sort of cap this off uniquely with discs inside of the four ball or the zero handle. Up top, capping that off is a little bit more complicated. You have to think a little bit more carefully about that, because that top link is going to live inside some is going to live inside the boundaries, the boundary of the boundary sum of a couple. Well, maybe I'll write this down. So we cap off. We're going to cap off the link components in B4, which is really just our zero handle, with discs. Okay. And then we're going to cap off the surgered link inside the boundary sum of S1, B3s. So this is really like our three handles union our four handles. And so we can also, so down here we have sort of the original link. We're capping it off inside the zero handle with some discs. Here we have our banded link. We perform surgery along there and then extend that upward. And then finally we get to that 5/2 level, and then we cap it off inside the 3 and 4 handles with discs as well. Okay. So it takes a little bit more work, and this is going to be one of the homework exercises to see that boundary parallel discs inside an object like this are unique up to isotopy. So just like in the four ball, there's sort of only one way to cap off a bunch of unlinks or cap off an unlink with a bunch of boundary parallel discs. There's also a unique way to do that inside the 3 and 4 handles. Okay. So maybe I'll pause there for questions.
You're saying we can interpret the banded unlinked diagram as being in any of the three?
Yes.
So what you're saying here no matter which of the three levels you're interpreting it, that's where we're capping off L and LB.
Well, so this banded unlink we can kind of think of as living anywhere between 1/2 and 5/2. Okay, and implicitly what we're doing is we're using the Morse function. We're using the gradient flow of the Morse function to identify these levels, which you can do away from some manifolds that get you in a little bit of trouble. And I'll talk about that in a second. But so we sort of think of this banded unlink as living in all sort of levels between 5/2 and 1/2. And then at the bottom, we're capping it off with disks in the 0 handle. And at the top, at the middle point, we're doing surgery.
Okay.
And then at the top, we're then capping off with
Okay.
disks in the 3 and 4 handles.
We're always doing the surgery part in, okay, I understand.
Yeah.
And then another thing is you said when we draw it, we want to draw it, like when we draw the banded unlink diagram in the Kirby diagram, we want to stay away from the attaching regions.
Yes, yeah.
What exactly do you mean by that? Because in your other picture,
Yeah.
like.
Oh.
Yeah.
Yeah, so that band goes over the one. So yeah, so we want to, really what we want to avoid is not the attaching regions, but the actual links themselves.
Okay.
And so the dotted one handle circle, you're right, that band is going up and over the one handle, and that's okay that it's passing through that attaching region. But we actually couldn't have a link component do that as either. So bands can do that, but link components can't.
Okay, so bands can do that, link components can't. And the reason we want to avoid the links in the Kirby diagram is just because then we don't know how to interpret it,
Why we want to avoid links,
or like why we want to avoid the Kirby.
Yeah, why we can't have a black
Yeah.
black arc go through there. It's because so essentially what's going to happen is we want to push this down past the one handle. And if that link component goes over the one handle, when we sort of go down past the one handle, it sort of the one handle dissolves and the link component would kind of get stuck. So
Yeah, I think I see. Okay.
Okay.
Thank you.
Other questions? Yeah.
I have the same question forward. There you said that you can present that LB is within either of the 300 components.
Pardon me?
So like the second line says think of LB as living in any of these three manifolds.
Yeah.
But then you just said that the bands can only be attached after we attach the one handle, so they can't live in M1/2.
Oh, okay. I see what you mean. Yeah. So yeah. So you're right. Is there a better way to phrase this? Well, it's just that the point is the bands can go over the one handles, and so I guess really technically what we're doing is we're using the gradient flow of the Morse function to identify sets at different levels with each other, which is essentially what we were using the height function for in standard banded unlinks. And so technically you're right. We don't want to push the banded unlink everywhere up and everywhere down. The only thing that we're pushing down are the unlinked components, and the only thing we're pushing up is the surgered link, if that makes sense. So this statement here is, I don't know how to make it exactly precise without maybe writing out more than I probably want to write out, but you're exactly right. We don't think of this banded unlink as living at all levels. We think of the unsurgered link as being pushed down, and it sort of lives between 3/2 and 1/2, and the surgered link lives between 3/2 and 5/2.
But so if you're not allowing your link to go through the one handle, aren't you losing some surfaces?
Well, the link can go like the surface can kind of go through the one handle, but essentially all we're doing here is we're sort of pushing our minimal disks down to this level 1/2. And so the minimal disks are, sort of just they don't interact at all with the one handles. And so they can't go over the one handles for the very reason that if you were to sort of go down past them, if they went over the one handle, they'd be stuck there and the one handle would dissolve. But the link, the surface itself can interact with the one handle via the bands. And so after you do the band surgery, your surface can definitely sort of link the one handle, yeah.
Then you allowed the link L to be linked with the two handles. And so I guess you're saying that you can just attach the two handles later and everything is okay.
Yeah, so the two handles are kind of glued on, like if the link and the bands can be sort of, situated, and the two handles are then sort of glued on after that happens, so they can link the two handles for sure, yeah. Yeah.
If we want to move it on the picture we already have, are we able to treat like the L as like a two handle and do curvy moves with it?
Yeah, so I'll talk about like the moves that we get, and we do get a lot of things like handle slides and band slides over handles and stuff. So we get an expanded list of like handle moves and surface moves, yeah. Yeah.
How do you ensure that the surgical link bounds discs in the two?
Oh, so that is something you have to check. So a banded unlink, I guess I'll make a definition here. A proper definition. A banded unlink diagram in our Kirby diagram K is a triple K L bands. So just like in our format or in our S4, and we want, so with the following properties, okay? So we want the link union the bands to live in the exterior of the Kirby diagram that we've drawn. We want L to bound disjoint embedded discs in M1/2, and we want the surgered link to bound disjoint embedded links, embedded discs in M5 house. Okay, so just like a banded unlinked diagram in S4, not every link you draw, not every unlink you draw plus bands you fill in are going to give you a surface. You have to check that after you surgery it, it's also an unlink. And these are sort of the conditions. You want it to start off as an unlink, and you want it to sort of be an unlink in some surgered 3 manifold that you obtain after doing your 0 or 1 and 2 handles. Yeah.
For example, if you have a really messy Kirby diagram, after you do the band surgery, how do you ensure uniqueness? Like, it might bound a bunch of different discs.
So this will be sort of an exercise, like so boundary parallel discs in the 3 and 4 handle are unique up to isotopy within the 3 and 4 handle. So the discs you might get if you really do cap them off just in this 3-dimensional level, you could get different families of discs that cap them off. But if you're willing to sort of push them into the 3 and 4 handles a little bit, they can be isotoped to match each other. So it can be done uniquely. Rel boundary is important. We want to fix the boundary, of course. Yeah. Yeah.
I think you mentioned some conditions that L and B must satisfy so that it actually can be thought of as a banded link.
Yeah.
Can you explicitly that?
So these are the conditions here. Essentially, we want the bands and the link to miss the decorated link that we think of as being our Kirby diagram. We want L to bound to be an unlink. Essentially, when you ignore the 2 and 1 handles, you want L itself to be an unlink, and you want the surgered one to be an unlink in this 3 manifold here, which is really just a surgered S3, where we've done our 0 handles, we've done our 0 surgeries corresponding to the 1 handles, and we've done our Dane surgeries corresponding to our 2 handles. So yeah, I don't know. So those are like the conditions that need to be satisfied for it to define a surface.
Can it be written in terms of the band, or we have to check that the third condition called returning to? Is there a kind of sufficient condition that when we draw?
I think you need to check.
Yeah, there's not like an easy sufficient condition. Yeah. In S4, it's nice you just do the surgery, and generally you can sort of see when that's gonna give you an unlinked, but
Even here's sphere, just draw the random diagrams. How do you know it is unlinked?
that's true, yeah.
It's really hard. It's
Yeah.
actually a really hard problem, even for just the unknown, like detecting whether it is an unknown. Not a simple question.
Yeah, and here now you have, I mean, really your unlinked lives inside of connect sum of S1 cross S2s, right? And so now it's, the situation is, you know, you still need to check that this is actually an unlinked that can be capped off correctly. Yeah.
Another question, returning to of the uniqueness problem. All of this happens currently in your definition in a closed manifold where you have 3 and 4 handles.
Yeah.
Not ensures uniqueness. If I want to just do a similar analogy in, let's say, 2 handle buddies, where we no longer have 3 and 4 handles, but for some reason I still want, let's say, 2-dimensional 2 handles both surfaces, does that just don't have uniqueness?
You need to specify.
Yeah.
So I have to specify.
Yeah, if you don't, because so I think yeah, what I was trying to explain earlier is like within that 3-dimensional level, your disks might not be unique, but if you have that 3 and 4 handles to push into, you can make boundary parallel disks isotopic rail boundary. If you don't have the 3 and 4 handles, then they're not uniquely determined by just the boundary link. Yeah, it's a good comment. So yeah.
So I'm slightly concerned because there's an asymmetry here. It seems to me that M1 half should be due to more like M7/2. Do we make this choice artificially so that it's more adapted to our Kirby diagram?
Yeah, I guess we never really tried to make it symmetric with respect to the heights. I assume that you could by sort of pushing your disks up into the 4 handle. And you could maybe then sort of think of the band surgeries happening right at level 2. But that's not usually how we sort of, yeah, I think it's more adapted to how we usually think of a Kirby diagram which has an asymmetry kind of naturally, the way we think of them usually.
And basically, you also can change the conditions, like, you know, we're using M1/2 and then M5/2 there, but you can actually change it to M3/2 and then M7/2.
Yeah,
it doesn't really matter.
Yeah, you can kind of push the bands up to that. I mean, you could push the bands up to M2, and you could push the maximal disks up to M7/2 if you wanted to. But yeah, so there's not really a reason why you couldn't do it that way. I've only got like 2 minutes. So let me get to the moves. Okay, so I didn't talk about, I promised to talk about sort of like the Morse function. Essentially, on how do you then come up with the moves to sort of relate diagrams like this? Okay, well, so our Morse function H, let's say negative nabla H, okay, is a vector field on X, which we can think of as flowing down X. Okay. In the notes, there's sort of a little bit more details written down here. But for every critical point, you have what's considered what are called the ascending and descending manifold of a critical point. So I'll just draw sort of what this looks like for a 1 handle. Okay. So for a 1 handle, you know, if we think of our critical point here as being P, okay, if we look at the flow of nabla H or negative nabla H, we get a vector field that's sort of within the co-core of the handle. I didn't describe what a co-core is, but it's sort of this middle slice of the handle. The vector field negative nabla H is the negative gradient is flowing into that critical point. And then you also get sort of part of your vector field away from that co-core, kind of looks more like this. Okay. So if we look at sort of all points that would eventually flow to the critical point, that's called the ascending manifold or the ascending manifold of the critical point. And the points that are sort of, if you were to reverse time, would eventually be flowing towards the critical point, that's called the descending manifold. Okay. Now, oftentimes these are called like stable and unstable, depends on what your preferred sort of terminology is. But so the ascending manifold, you can think of that as kind of just being the co-core of the handle, and the descending manifold is the core of the handle. Okay, so here this would be like our descending manifold, and our ascending manifold would be the co-core, because every point in the co-core is flowing towards P. Okay, so the point is that with this negative gradient, with this gradient here, we can use this gradient to sort of flow points from one level of our manifold down to another level, provided that we're not picking a point that lives on the ascending manifold of a point that we're going to pass. Okay, or if we want to flow a point up our manifold, as long as we're not passing, as long as we don't live on the descending manifold of a critical point that we're going to pass, we can sort of make these identifications just using sort of standard Morse theory arguments. Okay, and so the idea is if we start off with a banded unlink, and we want to, or suppose we start off with a surface, an embedded surface that has some saddle points, some saddle bands, some max and min points. We want to sort of push all our saddles down to the correct level. Well, we can do that. We can push them down, but if we start off with a saddle that lives above an index 2 critical point of the manifold, when we pass it down, we run into some potential ambiguities. Okay, I'll show you this here. So suppose we have a band that we want to push down, but it hits its. We want to push a band past a 2 handle, but suppose that band intersects the ascending manifold of that 2 handle. Well, then when we push it down, we're going to run into a situation where this band goes up and over the 2 handle, and we don't want that to happen. We want to be able to sort of push it completely past the 2 handle. So if our band intersects the ascending manifold of our 2 handle, we have to make a choice, and we have to push it either to the left or to the right to push it off that ascending manifold. Likewise, if we have a band that we want to push up, if that band intersects the descending manifold of a 2 handle and we're trying to push it past that 2 handle, then we run into the situation where once we push it up to the level where the 2 handle is attached, the band would then intersect the 2 handle attaching circle, and we have to make a choice to either push it sort of to the left of the attaching circle or to the right of the attaching circle. Okay, and likewise with sort of 1 handles and things like this sort of rearrangement of bands, we run into trouble whenever we're trying to pass a critical point and we sort of intersect one of the ascending or descending manifolds. And so when that situation happens, you have to make a choice, and up to isotopy, these choices can kind of be captured by these band moves. And so, for example, what this tells us is that if I have 2 banded unlinked diagrams for a given surface or for a pair of isotopic surfaces, we can always pass from one to the other using a sequence of these types of band moves. Okay, and if you have sort of an isotopy between 2 such surfaces, you can sort of break this isotopy up into sort of horizontal and vertical parts, and sort of show that your entire isotopy can kind of be captured by these sorts of moves. So I'm out of time, so I'll stop there. The problem section is going to have a few examples like this where you identify a surface inside a manifold and then try and realize some isotopy. So these are up on the Google Drive. So when you're doing the problems, if you want to refer to like this theorem statement and these moves, you can. Okay. Oh yeah.
So which surfaces can you have banded unlinked diagrams in an arbitrary format?
Any closed surface, orientable, non-orientable, but we do want it to be closed. We did think about the relative case, and you could write down the relative moves as well, but it gets kind of messy. So
it's not necessarily non-homologous or something.
No, any embedded surface.
Any embedded
surface. Orientable, non-orientable, genus, no genus.
The existence of the
Yeah.
The
moves and like the description gets just a little bit notationally really messy. So.
And also just a comment is after our work, I think Maggie and Patrick was actually also describing the same thing for the non-oriented surfaces, closed non-oriented cases. ambient matter can be lunar.
Yeah,
But I don't remember the moves, but. it
Yeah.
also-
And another really nice variation as well is the variation with immersed surfaces.
Oh, yeah. So we have a paper where we do immersed moves, and the way you handle self-intersections is using these thickened vertices. So you can do immersed things as well and talk about regular homodylics, etc.
I'm not quite sure how like the data of like how the surface is embedded is preserved. Like for example, if the surface goes around some element of pi1 or like H2, like how do you know how do you know you can do these isotopies without like breaking that, because that surface can't just go willy-nilly wherever.
Yeah, so I think like for example, pod one here, notice you can like slide like really under the one handles. You can slide bands or link components under the one handles, but you can't sort of take a band that doesn't link a one handle and then make it link a one handle, unless you're sliding over some already existing two handle or something like that.
Okay.
So yeah. So the moves don't allow you to like break the topology. Yeah.
So in the picture, you drew the bands in the 3/2 level, but when we consider those moves, we think of the moving the bands maybe in 1/2 or maybe go above 5/2 and then go back to 3/2. In that move, you said, I think you said things like pushing the band
up past the handle.
Yeah. So does it mean you're not fixing the band to be stayed on level 3/2?
Well, when we write down a diagram, we're sort of assuming the bands are at level 3/2. But you're right. I mean, your surface could have started really weird with bands that are really high up or bands that are really low down. But the idea is we want to sort of push them to this middle level, and so it's really pushing them past those critical points that are in between that we really need to concern ourselves with.
So that's what's going on in that.
Well, maybe just in the interest of, is it okay if we talk? Because I'm worried that I'm already over. So, but I'd be happy to continue this. I don't want to take from Aru's time. So, is that okay if I self-censor and cut myself off? Okay.